Properties of electric charges. Let us begin by outlining the key topics we will cover regarding the properties of electric charges. First, we will examine the existence of the electric force and how it can be easily demonstrated. Following that, we will discuss the two kinds of electric charge that occur in nature. We will then move on to two fundamental principles that govern electrical interactions: the conservation of electric charge, which explains how charge is maintained in an isolated system, and the quantization of charge, which details how electric charge exists in discrete, fundamental amounts. These core concepts will form the foundation for our ongoing study of electrical phenomena. We can observe the existence of the electric force through a number of simple, everyday experiments. For example, if you rub a balloon on your hair on a dry day, you will notice that the balloon can then attract small bits of paper. Sometimes, this attractive force is actually strong enough to completely suspend the pieces of paper directly from the surface of the balloon. When materials behave in this specific manner, they are said to have become electrified or electrically charged. The interaction you are observing here is due to the electric force, which is precisely defined as the force acting between these electrically charged objects. In addition to the attractive forces we just discussed, an electrified body can also exert repulsive forces. The photograph here demonstrates this effect quite clearly. When a person's body becomes electrically charged, that charge distributes itself. Consequently, each individual hair on her head receives a similar charge. Because these electrical charges are of the same type, they exert a repulsive force on one another. This causes the individual hairs to push away from each other and stand straight up. This provides a very visual representation of how electric forces can push objects apart. Continuing with the effects of the electric force, let us look at another example of an attractive force in a common scenario. The image shows a cat that has been playing inside a packing box filled with styrofoam peanuts. By rubbing against the styrofoam, the cat's fur becomes electrically charged. As a result of this charging process, an attractive electric force is generated between the cat's body and the peanuts. This electric force is what causes the lightweight styrofoam pieces to stick completely to the cat's fur as it exits the box. Through various historical experiments, it was determined that there are exactly two kinds of electric charge. Benjamin Franklin was the individual who named these two types of charges positive and negative. At the fundamental atomic level, we identify electrons as the particles having a negative charge, while protons are the particles that are positively charged. To standardize how we discuss macroscopic charged objects, we utilize Franklin's convention. According to this established convention, when a glass rod is rubbed on a piece of silk, the glass takes on a positive charge. Conversely, when a hard rubber rod is rubbed on a piece of fur, the rubber takes on a negative charge. Now let us examine exactly how these different electric charges interact with one another. If we take a negatively charged rubber rod and bring it close to a positively charged glass rod, we observe that they exhibit an attractive force, pulling toward each other. However, if we bring two negatively charged rubber rods close together, or conversely, two positively charged glass rods, they exhibit a repulsive force and push away from one another. This leads us to a fundamental conclusion governing electric forces. Charges of the same sign will always repel one another, and charges with opposite signs will always attract one another. The figures on this slide visually summarize the charge interactions we just defined. In the first scenario, labeled A, a negatively charged rubber rod is suspended by a string. When a positively charged glass rod is brought near it, the force vectors, labeled with an E, F, point inward toward each other. This indicates that the rubber rod is attracted to the glass rod. In the second scenario, labeled B, the suspended negatively charged rubber rod is approached by a second negatively charged rubber rod. Here, the force vectors, F, point outward and strictly away from each other. This clearly demonstrates that the suspended rod is repelled because they carry the same type of charge. An extremely important aspect of electricity is the principle of conservation of electric charge. This principle states that total electric charge is always conserved within an isolated system. When you rub one object against another, such as glass on silk, electric charge is not actually being created. Instead, the newly electrified state occurs entirely due to a transfer of charge from one object to the other. Consequently, one object gains a certain amount of negative charge, while the other object gains an exactly equal amount of positive charge. This is logically possible because ordinary, neutral matter naturally contains equal numbers of positive charges, the protons, and negative charges, the electrons. This diagram provides a clear visual representation of charge transfer by rubbing. As we can see, when a glass rod is rubbed on a piece of silk cloth, the physical interaction causes electrons to be transferred directly from the glass material to the silk. Because electrons inherently carry a negative charge, their movement means the silk cloth obtains a net negative charge. Since the glass rod has lost those exact same electrons, it is left with an equal magnitude of positive charge. This perfect balance between the negative charge gained and the positive charge left behind perfectly illustrates the fundamental conservation of electric charge. Another fundamental property to understand is the quantization of charge. In 1909, physicist Robert Millikan discovered that electric charge does not exist in arbitrary amounts. Rather, it always occurs strictly as integral multiples of a fundamental, indivisible amount of charge, denoted by the letter E. Because of this, we say that electric charge, represented by the variable Q, is quantized. This is expressed mathematically by Q equals plus or minus N times E, where N is an integer. Looking at fundamental atomic particles, an electron has a charge of negative E, a proton has a charge of positive E, and a neutron possesses no electrical charge at all. Let us test our understanding with a quick conceptual scenario. Imagine 3 objects are brought close to each other, 2 at a time. When objects A and B are brought together, we observe that they repel each other. Similarly, when objects B and C are brought together, they also repel each other. Based on our established rule that only like charges repel, we know that objects A and B must absolutely share the same sign, and objects B and C must also share that same sign. Therefore, all 3 individual objects must possess charges of the exact same sign. This tells us that statement C, stating all 3 possess charges of the same sign, is the correct and true conclusion to draw. To summarize what we have covered, we established that the electric force is the specific force that acts between electrically charged objects. We learned that there are precisely 2 kinds of electric charges, positive and negative. A fundamental rule governs their physical interaction, like charges will always repel each other, whereas opposite charges will always attract each other. Furthermore, we discussed 2 vital physical principles. First, electric charge is always conserved within an isolated system, meaning charge is only transferred from one object to another and is never created. Second, electric charge is strictly quantized, existing only as integral multiples of a fundamental charge, E, defined mathematically by Q equals plus or minus N times E. Before we conclude this module, here are 2 review questions for you to consider and work through. Question 1 asks you to explain the process of charging by rubbing at the atomic level, and to specifically describe why this process fundamentally supports the principle of conservation of electric charge. Question 2 asks, if a physical object is measured to have a net charge of -3 E, what can be logically inferred about the total number of electrons relative to the number of protons in that specific object, based entirely on the principle of charge quantization?